Hi, everyone. Welcome to one more webinar of our ASTRAIOS webinar series. The ASTRAIOS is an EU-funded project which is working on identifying the existing space-related education and training across Europe, projects the future demands for space skills from the European space industry, and identify the actions to align and improve the career pathways into the sector. So the project, there was something in the chat. One second. Okay, sorry everyone. I thought it was a problem with the audio or something like that. So the project started in January 2003 and spans across 3 years. And now we are heading to the final year of the project. And this webinar is part of this final part where we are helping on reach the goals of improving the existing training material and developing new ones to fill the gaps that we identified between the supply and the demand for the space education and training courses. So, in today's webinar, we will discuss large-scale glacier monitoring with Earth observation and deep learning. And thanks a lot to our guest speaker, Konstantin Maslov. Konstantin is a PhD candidate in the Department of Earth Observation Science at the University of Twente in the Faculty of Geoinformation Science and Earth Observation. So, Konstantin, thanks a lot for joining this webinar, and I'll hand the floor to you to start this great presentation, and let's learn a bit more about this topic.
Okay, thank you. Hello, everyone. As it's been said, my name is Konstantin Maslov. I'm a PhD candidate at the University of Twente at ITC. I'm finishing my PhD this year. And I'm mainly working with glacier monitoring with Earth observation data and deep learning. So today I will talk mainly about my PhD journey, about what I did during my research, 4-year research. So research is funded by the Research Council of Norway, and we have a very strong collaboration with the University of Oslo, where our PI is located. And our project team mixes different expertise from deep learning, from glaciology, from spatial statistics. And me, myself, have some experience in IT and information systems, sort of software developing things and machine learning. And additionally, we got funding to do this research from Cloudflare and Ocre, which provided computational resources to perform everything we did. Otherwise, it wouldn't be possible. So my PhD is about large-scale glacier monitoring with Earth observation and deep learning. And I will mainly talk about retrieving two important products for glaciers. The first one is glacier area, and the second one is surface mass balance. So we know that glaciers are an essential part of climate and ecological systems because they are very sensitive to the small fluctuations in precipitation and temperature. And because of that, we can use them as a good indicators of what's going on with climate on the Earth. They are strongly related and linked to sea level rise. And currently, in the last decade, the contribution of mountain glaciers to sea level rise alone is comparable to the contribution from ice sheets. They also serve as a very important reservoir for water resources, and they provide water for irrigation and for drinking in many areas of the world. And in some areas such as Andes and the Himalayas might be important in special seasons where without glacier runoff it would be very dry otherwise. Of course, they're related to changes in ecosystems, and glaciers themselves are highly interesting ecosystems on their own, and so you can see very interesting biological things going on glaciers. For example, in this picture, you can see algae bloom on the surface of glacier, which makes snow looking green. And also they are related to hazardous events, mainly GLOFs, glacier lake orbits floods, where a lake is formed next to a glacier, and then glacier serves as a dam, and once this dam collapses, a lot of water gets released, and it can have disastrous consequences for the villages, for the settlements located downstream. So glaciers are changing, and we would like to better quantify how they change and predict this process. And because of this, we need good data. And we need good data in terms of observations, and we need good data in terms of forecasts. That's technically the reason why we propose this project called Massive Machine Learning Surface Mass Balance of Glaciers, Stone Cover, in-situ data, volume change in Earth observation. And what we aim to do is to provide these essential data sets to the wider scientific community and to the public. And what outcomes we expect to have by the end of this project is multi-temporal glacier inventories, a multi-annual time series of mass balance, change analysis of glacier area and mass balance, and of course benchmark data set for the deep learning community to further develop the models that we propose here. So my part is about glacier outlines, glacier area, and about surface mass balance. So glacier area, we can retrieve it from glacier outlines. So if we know where the boundaries of glaciers are located, we can calculate the area. And so we have several databases where we have these outlines hosted. The biggest one is GLIMS, Global Land Ice Measurement from Space. And it technically provides you with global coverage for all glaciers in the world. And it can also provide you multi-temporal data. But the problem with this data set is that there are very annoying uncertainties inside. So different glaciers at different times were mapped by different people, and hence the data products are not really suitable for area change analysis. There is a subset of GLIMS called RGI, Randolph Glacier Inventory, which is also global. It's more consistent, and it provides you with one time step of glaciers in time, approximately in 2000 years. And there are also several papers which provide you with regional inventories here and there, but technically they suffer from the same problem with consistency. And mapping glaciers, especially if you want to automate it, presents unique challenges. And if you want to automate it everywhere at any time, it becomes even worse because we have generalization issues. So it's very difficult to propose one method which works in different environments, in different climates, in different times, in different sensors of satellites. So what we did is we tried to collect as much data as possible to put it into deep learning to have a model which sort of works everywhere, anytime. And we hope that these models will serve as backbone for producing inventories and also for producing more complicated, more advanced models for glacier outline retrieval. And in these pictures, you can see some examples why glacier mapping is complicated, especially. In the picture top, you have glacier, which is covered with a layer of rocks and debris on top. Technically, everything beneath this layer of rocks is ice, and we want it to be mapped as well. But it's difficult from optical data only because spectrally, these rocks are very similar to the rocks at the edges. And there is even more complicated scenario like this one. It's Malaspina Glacier in Alaska. It's a very unique glacier. And what we can see there is that there is a layer of soil formed on the surface of glacier, and that there are even forests which developed on top of this. Technically, we also want to map this glacier because it's part of the glacier, and this becomes even more complicated. So let's say we move to the first sub-project of our larger picture. We call it globally scalable glacier mapping by deep learning matches expert-donation accuracy. And what we did here, we collected as large data set as we could collect. So it's 500 gigabytes of data and includes approximately 9 glaciers worldwide and covers 7% of glacial area also worldwide, excluding Greenland and Antarctica. It's multi-temporal. We span from 1988 to 2020. It's very diverse. We have included glaciers from different environments, from tropics to polar, from dry climates to relatively humid climates, glaciers which are alpine, glaciers which are terminating in sea. It's very heterogeneous because we also mix different sensors. Mainly it's Landsat mission, Landsat 5, 7, 8, Sentinel-2 from the optical. And we also included SAR data, which is Sentinel-1 mainly, and also some acquisitions from Envisat. We structured this dataset, so all areas of interest in this dataset were divided into near square tiles 10 by 10 kilometers squared, and we randomly split it into 3 subsets. One we used for validation, one we used for testing, and another one, the largest, we used for training the model. And we also selected a completely independent dataset for a completely independent performance test. And it's an important part of the story because actually, when we talk about autocorrelation, our data set, it's not only about the space, but it's also about time and sensors. And the conclusions that we made on the testing side from this structured data set and completely independent test set are slightly different. So here's an overview of the coverage of the data set that we collected and also the performance that we see on these structured tiles. Overall, you can confirm that indeed the coverage is pretty broad from Antarctica to Svalbard, from Alaska to New Zealand. And you also can notice that we overall have very nice performance, which is encoded here with IU. We have generally IU higher than 75%, except one region, which is High Mountain Asia, which is a complicated one where we have a lot of debris cover types. And we also don't have a really good reference, updated reference for steers. So what was the model, how we did the mapping? I will not go into technical details a lot, but we used Glacier Vision Transformer Unit in Glavitu. So the idea was to combine transformer with a unit, because we know that transformers are very good at capturing global context of images, and unit is very good at restoring the fine-grained details. And we want to have the advantages of both. So technically what we did, we just stacked the models together. And we explored several strategies about how to train this model, because when you have a lot of domains, a lot of sources of data, it becomes not so straightforward how to actually train the model. So we explored strategies such as global, where we just put all data into one model and hope that it works. Then we trained one model per region. Then we took the global model, fine-tuned it for region. And then we explored sort of global model, but with included coordinate or region information. And a lot of part of the story makes the uncertainty quantification. We are always trying to quantify the uncertainty of our modeled results, not only in terms of accuracy, how it corresponds to the reference, but also in the sense how model is confident about its predictions, because then we can actually claim whether we observe significant changes or not. So here's the results on the completely independent test acquisition dataset. So here we have mixed conclusions, but technically what we can find is that the global model, where we just put all the data into one model, works best, or region encoding with some small tweak for domain adaptation slightly outperforms the global data, but it's not really consistent. In some cases, global works best. In some cases, region encoding with a bit of domain adaptation works best. And we also have comparison against bend ratio. It's a classical remote sensing method for detecting ice, where we just put the threshold on a bend indices. And obviously, deploying outperforms it everyone. So here's a qualitative overview of the results. What you can see here is how our predictions are matched with the reference. Those are shown in yellow. And you can also see the predictions of bend ratio, but expectedly it fails completely to predict debris cover types. And yeah, we still have some problems in some places, sometimes with debris and sometimes with ice melange. So in this case, in Alaska, where we have glaciers flowing into a fjord and we have very active ice formation, we cannot really distinguish the glacier float from the rest, but this problem was solved later with another method that I will talk about in a bit. And as you can also see, we always report these confidence intervals. It's not only the prediction of the model where it puts the boundaries, it's also this reddish area about where the boundaries are likely to be. Here you have more numbers about how good the model is. But what is important here is to compare the pixel size that we had from Sentinel-2 or from Landsat missions against the median distance deviation between the boundaries of the experts and the boundaries from our model. And you see that in all cases for these 17 glaciers distributed in everywhere, it's a mix of several regions. You can see that generally our deviation equals one median, our median deviation equals one pixel size, which allows us to claim that actually the performance of the method is comparable to the performance of a human expert because they obtain the same numbers. And also we are very close, well, technically we are exactly in the same part with human experts in terms of area deviation, percentage area deviation. And what we also wanted to show with this method is that we can actually detect significant changes at the decadal scale. And here you can see some examples of it. The left part, the left 3 columns is from the European Alps, from the Swiss Alps, where we have a lot of debris and where we have retreat of approximately 1 kilometer for different glaciers over 20 years. And the second example is from Norway, South Norway, Hardangerjoklen, where we also have no so dramatic change, but still we can find with our model that it was significant. And just an interesting observation, you can see how the presence of water bodies affects the speed of glacier retreat. So this glacier was located just next to the ice lake, to the lake, and because of the water being very strong heat reservoir, the retreat for this Germany is much more than for the rest of the small ice cap. But then the problem is still there because we rely so much on optical data. We cannot really go to high temporal resolution for the glacier outlines products. And what we did here, we tried to question ourselves. Is it possible to map glaciers from SAR data only? Because SAR data is not affected, mainly not affected by weather. And we can have very dense acquisitions from 2015, 2016, where we have Sentinel-1 launched operationally. And so we questioned this question and we asked this question and we tried to do something, and we selected an area, it's Svalbard, it's a Norwegian archipelago in the Arctic. We applied the method there, and what we found is that there is 3 times accelerated glacier area loss in Svalbard. But let's go back to the idea. So if you look at the time series of SAR for glaciers, you might notice that in summer backscatter goes down dramatically because of the melt and because of the change of the backscatter mechanism. And in-SAR coherence generally remains low for glaciers throughout the year because glaciers are moving by definition. And so that was our motivation. What if we can just put this text into a very simple deep learning model? Would it be able to extract glacier outlines out of it? And surprisingly, well, not surprisingly, but the good news is that it's able. So what we did here, we took Sentinel-1A data, covered almost the whole of the archipelago, and so we have two stripes of acquisitions. One is in the west, one is in the east. And out of there, we can extract approximately 700 square tiles, 10 by 10 kilometers, and we structured in a very similar way. We use 60% for training, 20% for validation, 20% for testing. And we use two glacier inventories to train the model. One is from 2016, 2017 from Frank Paul. Another one is from 2020. It's from Norwegian Polar Institute. And what we did here, we took a very simple unit. So if you're familiar with the unit architecture, it looks something like this. But we did very small but important change, because the original unit can only operate in spatial and, let's say, spectral domains, but it doesn't know anything about time. What we did here, we changed the encoder part of the unit to the temporal encoder by replacing two-dimensional convolutions with three-dimensional convolutions. And in this way, the model treats time in exactly the same manner as it treats x and y coordinates. So we have convolutions which are 3D and which work in spatial and temporal domains simultaneously. We also explored different feature setups. We tested just GRD data, just RTC data, radiometric terrain corrected SAR data, which is GRD data but corrected for the pixel size, which is different due to the layover effects. And technically, it's normalized backscatter, because for larger pixels, you will have higher backscatter in GRD, the pixels which face the sensor. And otherwise, if it faces another direction, it will be lower GRD on average. This one is trying to flatten it. We also tried to use INSAR only, and of course, combinations of GRD and SAR, RTC and SAR. The best combination which we found is GRD and SAR, which gives you almost no difference with RTC and SAR, but still good, because processing GRD is just faster, and we know that we can make fast processing and still get results which are the same in terms of the quality. This is very small technical detail, but we played a bit with how we do pooling. We propose this time-weighted pooling block. And what we found is that by doing so, we just improve the convergence properties of it. So here's the results. You can see how good is the model, how it matches with the actual outlines for the experts. On average, it's good, yet we have some problems with the little small ice tributaries like here. And some inconsistencies with how we map small ice bodies, but is debatable, because probably a lot of polygons mapped as ice in the 2016-2017 inventory is actually snowpacks. So yeah. And of course, as usual, as with the last work, we always report the predictive uncertainty of our model. So we still have this 95% confidence bands for every outline that we produce. And we did some additional external validation. So the first is the results of validation of internal validation are presented in this table. We have area deviations, which are still comparable with human experts, and we have median deviation, which is 1 or 2 pixels, which is on par with human experts as well. And we did external validation against completely independent Calvin font mapping data sets. So two of them. The first one is the data set from NPI, where people were delineating Calvin fronts. Calvin fronts is the ceremony of glaciers, which are located at the interface between ice and ocean. So when glacier flows into fjord or into sea, the front, which is formed where we have iceberg formations called Calvin fronts. And we compared the Calvin fronts from our model from 2016 to 2024 with manually generated data from NPI, from the Regional Pole Institute, and we got a very nice correspondence. And we also compared our data set against another deep learning product from people from TUM, and we found approximately twice better mapping ability. But of course, we do it only annually, so we produce only end of the ablation season from clients. In their case, they have a much higher temporal resolutions. They do it whenever they have good acquisition to do so. And here's the results in terms of what it looks like, spatially how glaciers changed. We have two maps presented here. The first one is comparison between Randall Glacier inventory, which is data from 2006 on average, against our first inventory from our model. And the second map is the comparison of the trends which we can obtain for each glacier from our model. And what is interesting here, what you can already see, is that 20 years ago, the change was mixed. Some glaciers were growing, some glaciers were retreating, some glaciers were growing a lot. For example, Austona, Basin 3, and Nutter Spring, but those are related to surges. And in the last decade, glaciers are mainly retreating, with some exceptions. For example, Austona Basin 7, which is also related to surge. So here we have two large surges happened in between 2006 to 2016. They temporarily actually offset area losses, and they actually affected the trend of the area change, making it very nonlinear because those events were large and dramatic. And the positive anomaly that we observe is related to another surge, and here you can have a small animation about what surge looks like. Surge is a sudden movement of glacier because of varying reasons. Some people relate it to subglacial hydrology. Some people related to some thermodynamics effects, but here you can see that somewhere in 2018, 2019, the front starts advancing fastly, and we can see on average increased backscatter, especially along the borders of this flow unit. So that's what the surge looks like from SAR time series. And then when we put all the results together, we actually found that the trend which we observed for the last decade, which is approximately minus 230 kilometers per annum, is 3 times larger than the trend we observed for 1970 to 2006, which we related as minus 68 kilometers squared from some available data sets and sampling schemes, but I'm not going into detail here. If we compare it to an old inventors from 1936, 1938, we can also claim that modern retreat is actually 5 to 6 times higher than it was back then. And we also confirmed, it was kind of known, but no one explicitly told it, that large surge events, such as Austona Basin 3, can affect the trend, making it nonlinear. And here is schematically shown these surge events and what was the influence of them on the trend. Interesting and good news for us is that we tried exactly the same approach in Greenland, and we can claim that we can map Greenland ice sheet even better than we can do Svalbard, but we can only confirm it for 2022. Hopefully generalize it to other years, and we can extend our analysis and provide glacier ice area change for Greenland as well. And now I'm going to link the previous work to surface mass balance because it's a bit different. And I will start still from a mapping exercise because there are some things on glaciers which we can detect and map and can relate to how actually glaciers lose or gain mass. And what we did, we tried to automate glacier facies classification, and to do so, we proposed pan-European dataset and the first deep learning baseline of this dataset. So technically, what we did, we were a group of 3 experts, and we took approximately 30 glaciers all around Europe from different regions, and approximately 90 optical acquisitions. And we distributed them among experts, and we told, okay, experts label the glacier facies that you can observe these optical images. And we did so, and on the right you can see the special distribution of the glaciers that we used and how we arrange the faults or cross-validations that we used in this work. We labeled 8 classes in total. Of course, it's ice, snow, firn is aged ice. We labeled shadows, we labeled superimposed ice is the ice which was refrozen within the snowpack when percolated and met this ice layer. It became cold enough to refreeze. Then we mapped clouds and water bodies, and also debris, of course. Of course, when you have this setup with 3 experts labeling hopefully the same things, but still with subjective judgment, you can have disagreement between experts what is actually what. And in this case, it can be dramatic because actually transition from snow to firn and to ice can be very smooth, and it's not always possible to agree for sure where is which class located. So to evaluate this effect on our results, we report the cross-expert agreement during the cross-check. And so you can see that, well, overall, all classes have nice agreement except snow, because a lot of snow was attributed, a lot of firn was attributed to snow initially. And then after the cross-check, so we rotated the faults between the experts and we said, okay, now sit together, check your labels, agree, disagree, discuss, and unify it as much as possible. So we did it as well. And here is the changes that we obtained after this realization. So what we did next, we trained a very simple VGG-like network, which is very shallow, very basic, to map glacier facies from these data sets that we collected. And what we also wanted to explore here is to use some data-driven AI options to actually clean the data set, because even after the cross-check, there is some chance that due to expert judgments or mistakes, there are uncertainties in the reference data. And to quantify them and to take them into account, we used a data-driven AI method, which is called confident learning. So the idea is technically you train the first suite of methods, then you run the inference, and then based on this inference, you can decide which label is confusing or potentially wrong and exclude it from the data set. So we did it, and here you can have some results. Not going to explain the numbers in detail. Overall, we have very nice delineation between accumulation areas and ablation areas of glaciers. Some classes like debris are almost perfectly mapped, at least qualitatively. But there were some failure cases. We'll stop on them a bit more. So the first one is Roriokal. Here we have a case where we had a very thin layer of clouds, which we labeled as clouds because it had, let's say, higher signal in short-wave infrared as compared to ice. And because of this layer being so thin, the model was actually confused and managed to label the actual facies, which were still observable beneath the clouds. So that was one of the failure cases, which we don't consider as actually failure. Then there was a very interesting case in Langyokal ice cap, where a lot of pixels which we labeled as snow were attributed to firn. And our working hypothesis is that maybe there was a thin layer of tephra of volcanic ashes, which reduced albedo and made the model confused, made these pixels darker. And this case is even more interesting. This is a case from the end of August, but apparently this acquisition comes just after the snowfall, and the whole glacier is covered with snow, but the model, because it's sort of biased to always have these clean images, at the end of the ablation season, where we have minimal snow coverage, get confused and produces a mix of all classes without coherent special patterns. And of course, as in previous works, we report the confidence for all classification maps that we get in the end. So as we mix different regions, it's also a good question how our model performs across the regions, as the problematic regions or other regions which are not problematic. Here we evaluated this, and on average, we would say that it's pretty stable, with the exception of Pyrenees, where we have only 60 labels in total, because we only have very small glacier, one very small glacier here in Maladeta. And technically, if you look at the number of samples we have there, it's very low. And that's why, how we explain why the overall number is so low. But in general, we have F1 score higher than 70% for all cases, for all regions and classes where we have more than 1,000 samples. And at the same time, the number of samples shows correlation with the F1 score of 63, it's peer correlation, and it's statistically significant. And if you calculate the performance not per region but per glacier, this is a number that we can get from this evaluation. It's approximately 80% of F1 score plus minus 12%. And what we also did in this study as additional external validation check, we correlated our products, classification products, with available surface mass balance records from WGMS, World Global Monitoring Service. So it's a database, well, it's an initiative which holds a database where you have surface mass balance observations submitted. And we did two evaluations. The first one on the left, where we trained one very simple linear model which relates surface mass balance to acquisition, area ratio, and snow line altitude. For all glaciers in our dataset, mixed and evaluated on the same fault structure as we used for mapping, which usually people don't do because these linear models are usually calibrated per one glacier, because every glacier has unique topographic and climatic conditions. But still, in this case, we found significant correlation between our results and the reference data, and actually acceptable mean squared error as well. And the second setting is where we took two glaciers where we have long enough time series and trained a similar linear model, and we found even better correlation on par with what people report in similar studies. So what's next? What's the next direction? What I'm going to do at the end of my PhD is to delve deeper into surface mass balance modeling, and what I'm exploring right now is TI model. It's temperature index model. It's a very simple model which counts the amount of days with positive temperature, and it technically, for every day, it computes the accumulation as a proportion of solid precipitation minus the melt term, and melt term is melt separately for snow, for ice, and there's separation between snow and ice based on different rules. In this case, what we did, we made this model AutoDiff friendly, which makes it possible to be implemented in Python frameworks such as TensorFlow, PyTorch, or in our case, JAX. And what we also did here, because it's AutoDiff friendly and it's already implemented in deep learning, we can actually introduce correctors for every parameter. So we can correct the parameter for precipitation, we can correct the parameters for melt. And these correctors are outputs of a very shallow, very simple deep learning model. But we use topographic data and aggregated climatic time series, monthly aggregated climatic time series, to sort of correct the original setting and to make our model more expressive and being able to grasp better patterns. So here you have a very short movie about how it works right now. It's on the scale of one glacier. It's Aletsch Glacier in Swiss Alps. So what we can see is that technically right now we have very nice correspondence between point measurements from the database, from the WGMS, and glacier-wide estimates. And overall warming patterns are well captured. If I move the movie, you can see that climate becomes warmer, and also the trend for the glacier surface mass balance becomes more accelerated. And what is also nice, the equilibrium line is consistent with glacier patches that we observed earlier. So if you look at this image, the line where the pixels are gray, so they're not reddish or bluish, is actually the line where you would expect to observe the snow line at the end of the ablation. And this is consistent with the results we had from the previous study from glacier patches mapping. And what is also an interesting point here for this particular glacier, well, it tells something about the data set itself, the reference data itself. We have evaluated our model against point measurements, direct measurements on glaciers, and glacier-wide, which is sort of model data. But it's very interesting to observe that on the point measurements where we should get like the highest quality data, we have negative bias of our surface mass balance, while for glacier-wide estimates, it's actually all positive bias. But anyway, so what we can do now with this model, which is autodiff friendly, is actually very interesting because once it's fully differentiable and autodiff friendly, we can write a couple of line of codes to solve problems like inverse modeling. And in this case, we ask ourselves what temperature change in 2015, 2024 is needed so glacier comes in equilibrium with climate in 2020, 2024. And to do so, you just define this loss function, which minimizes the square of surface mass balance. And for the years of interest, you run it with the same in the same way as you would do with training a deep learning model, but with regards to this temperature shift. And then you can compare it to situations. The first situation is here, is what we observed earlier. It's how glacier is evolving according to the current climate. And here we introduce this shift of delta T approximately -2 degrees Celsius, which we obtained from this optimization. And here you can see that in the last 5 years, it would be in equilibrium with the climate because of this. And of course, you can also see it on the map, how the equilibrium line amplitude changes because of the changing climate. And we can also have other benefits from this setup. The first benefit is seamless integration with other differentiable models, particularly with glacier dynamics models such as IGM, instructed glacier model, and ODIN. So technically, the idea is that we can combine both and have unified framework to model surface mass balance and dynamics in one go, because currently what people do, they use surface mass balance as external forcing for dynamic models. You can also do data assimilation from these corrections, technically what we can do already on the scale of one glacier. And what I'm working right now is I'm trying to fit one model that can generalize across glaciers because of these corrections introduced. And we can do more stuff like input attribution from explainable AI methods. Why for this particular glacier in this particular year surface mass balance was so low, and then we can attribute it formally to very high temperature, for example, during this year, or to very low precipitation. And so we can have first order aleatory conservative approximation to the model. So technically, the model can be written, decomposed as a sort of Taylor series, and then we can extract this first order certainty Fourier problem. So that's it from my side. If you have a question, I can answer it.
Thanks a lot, Konstantin. It has been great to see all this nice piece of work. So, yeah, and congratulations for the brilliant presentation. It was very nice. I have some questions here. The first, in the example of slide 6, when you showed the glacier where the ice is actually below the rocks and below some sort of soil, are the SAR data able to penetrate enough on that layer of soil in order to proper map it? And like in this case, is T-band enough? Do you need P or L band, or uh, uh, what is what are the capabilities of each star data for that?
Okay. Here I would not comment exactly on the wavelengths because I wouldn't know, to be honest. I can tell about C-band, and for C-band, just for penetration is not enough. So you cannot, definitely in this case, for vegetation, you cannot see it at all. And for rocks, it's also not possible. But what we rely on instead, it's not backscatter, it's in-situ coherence. So because it's still glacier, it moves. And if we take cross correlation between the phases of two adjacent acquisitions, we can detect the areas which changed or moved as glacier, or which remain stable, which are mainly like surroundings. If also, like in this case, it's surroundings. In this case, it's a bit more complicated because water is also low coherence. So yeah, we rely more on star coherence in this case, not on backscatter.
Okay. Thanks. For the next question is for the uncertainty estimation. Could you explain a bit better how do you do that? Because, for example, if we look back to the paper Paulo published in ASPRS on mapping the Brazilian savanna with uncertainty-aware models, he, besides the calibration, he actually included the uncertainty as part of the loss function. So he based on your method as well for that. And do you also include the uncertainty as part of the loss function, or do you do mostly the calibration with Monte Carlo dropout? How does that work?
So, okay, let's separate the stuff. First of all, we explore two different options. The first one is Monte Carlo dropout. So in deep learning, we have these dropout layers which drop randomly. And Monte Carlo dropout, the idea is that we can still keep its layer working during the inference. And because of that, we can run probabilistic inference and get a series of realizations. And from there, we can evaluate the uncertainty of the model. And the second one is we just take softmax score and we analyze how close the maximum probability to the threshold we use for classification, which is in our case 0.5 because it's binary for outlines. So in this case, when we compare both approaches, they are equal. We didn't find a lot of benefits from using Monte Carlo, which is good for us because we can make it just faster. Talking about loss function, uncertainty is sort of includes by designing any sort of function, because if you look at the cross correlation formula, it's technically cross entropy, which shows you how two different distributions are from each other. And if they are very close to each other, so if it's close to the decision boundaries, the cross entropy will be high, as compared to where it's confident and correct. And in our case, we go a bit further, we use FOFO loss, which actually penalizes the predictions which are less confident even more. So this uncertainty is included in this way. But we don't do any specific sampling, like we don't do like selection of the most uncertain sample. No.
But you produce the maps of because from I'm asking that because I've been working with Paul on that as well, and from what I understood, you do something like that as well. The uncertainty, the calibrated uncertainty that you produce is also useful for producing maps of where those maps, where the classification maps need attention. So in theory, where you have a wrong classification with low uncertainty, that's an area where low uncertainty means for the audience high confidence, which means the model predicts that area with a high confidence that the prediction is correct, but the prediction is actually wrong. And usually those areas are the areas that need more attention from an expert that would need to correct the maps. You produce also those explicit maps, right?
Yes.
Okay. And yeah, next question, following up on the methods themselves. In the slide 17, the previous one of these, you used the 3D convolutions in the encoder, but not in the decoder, correct? Don't you lose temporal information by not considering the temporal convolution also in the decoder?
We don't lose it, we compress it. So we partly lose it, of course, as always. But the point here is that our targets are not multitemporal. So we use inventories from optical data as training targets, and they are always produced at the end of the ablation season. So we have the sort of definition of glacier from GLIMS, which states that glacier boundaries are observable boundaries of a glacier at the end of the ablation season and all tributaries to the glacier. So it's the definition of glacier from remote sensing context is tied to the one particular time step of the year. So we produce only for this time step.
That's great. Thanks a lot. And the last question is more after the question was posted, you actually replied a little bit of that on your last slide, which now you are actually doing also the mass balance modeling and also modeling that more explicitly, right? And this you are doing with physical models, not with the deep learning models, right?
It's a mix. So we have the first model set up, which is TI model. It's a classical physical or mechanistic model, as you wish. But what we do, we make it AutoD-friendly, because in the original formulation, what they always do, they use these piecewise linear functions and they calibrate the models in like grid search manner. What we do, we replace these piecewise linears with very smooth functions, and we use gradient descent to calibrate these models. So that's the first point, but this is physical core. We don't use any deep learning here on the left. But then later, we put a deep learning model above it, and we put inside this deep learning model elevation of glaciers, glacier facies maps that we produced in the previous work, and monthly aggregated climate variables. And this deep learning model produces corrections to the parameters of the initial model. That's it. Yeah.
That's great. So thanks a lot. I will just share my screen here now with some more information about ASTRAIOS. We are coming now to the end of this great webinar. So for those who have more interest in our project, we have here in this slide the QR code for our social media. You can find all the webinars from this series in our YouTube channel. Together with the webinars, you can find that there are a lot of the material we have produced, interviews, and all the outcomes of the projects that were produced in video. You can follow us also in our X, that before was Twitter, and also on LinkedIn. And if you want more information about the project, this is our website. So thanks a lot, everyone, for joining. And again, thank you very much, Konstantin, for the great presentation and great contribution. Congratulations for your brilliant work, and thanks everyone. Bye bye.